welcome back to Tomography. So today we're going to go and engage in a different bit of mathematics. What we've done so far is we've taken a look at the Fourier method for obtaining doing image reconstruction from tomography, and this is really kind of the modern way of doing things. This filter back projection plus some of the signal processing type stuff that goes in there. And then after that, we talked about some more classical ideas, algebraic image reconstruction, which use the Castemar's method. And you notice I slur every time I say his name. I really have no idea. I should probably look it up somewhere. But so that was a classical method, which really comes down to solving algebraic equations like ax equals p. So what I'm going to do is I'm going to embark on a different direction that is sort of a blend between the two. So there are a lot of connections between, say, the Schwartz space and tempered distributions as sort of this core part of as part of a piece of what is called functional analysis. And what I'm about to present to you is another chunk of functional analysis, and it's called Hilbert Spaces. Now, Hilbert Spaces, they have the really unique property that they're a collection of functionals, where tempered distributions were collections of functionals over a Schwartz space. The collection of functionals over the Hilbert space is the Hilbert space itself. So it is sort of self-dual in a sense. And so we're basically going to be able to leverage this to make special functions later on when we talk about reproducing kernel Hilbert spaces, and we'll be able to make what I call occupation kernels. But today I want to go ahead and give you some really basics of Hilbert space theory, things like basic things about Rn or Cn and projections and whatnot, because all of those will be really important for us. And then in the next lecture, I'll introduce reproducing kernel Hilbert spaces, which are really core to all of learning theory, and they have a place in doing tomographic image reconstruction in dynamical systems. The application that my colleagues and I have put together is towards this idea of motion tomography, where you're trying to use tomographic samples to recreate fluid flows through the ocean. And so this allows us to, and so the occupation kernel method that we do, it basically does a sort of radon transform over something that's not a straight line. And so we get to incorporate dynamics together with these integral samples that we get, like the radon transform, in order to do a reconstruction of fluid flow. That's what these videos are going to be about, and building up to that. Now, this method can be applied to regular tomography, and we'll talk about that a little bit, and it is done in a very similar manner to what we saw with algebraic reconstruction techniques. So, in any case, alright, so I guess might as well go ahead and get started with it. Some of you guys might be fairly familiar with Hilbert space theory, especially if you come from physics. It's used all over quantum mechanics. And if you have a machine learning background, I mean, Hilbert spaces come up there too. I guess that's enough blabbering, and we'll jump into it.
Okay, so let's go ahead and get started. So we're going to be talking about Hilbert spaces today. And generally with Hilbert spaces, these are like something like the Schwartz space, where we had a metric on there, and the Schwartz space we saw is what we could call complete with respect to that metric. So if you ended up having a Cauchy sequence, then that Cauchy sequence would always converge. Hilbert spaces have the same property, but the metric that you get actually arises from something called an inner product. And so we should go ahead and start by talking about that. So an inner product on a complex linear space, and by the way, this is that text applied analysis by Hunter and Nottergale. So Nottergale. And so this is available free on their website. So if it's something you want to follow along on, it's easy enough to download. Let's see. Okay, I lost my space. So this actually appears in their chapter 6, and this follows what are called Banach spaces, which are a little bit more general of a space than a Hilbert space. Hilbert spaces are Banach spaces, but Banach spaces don't always have this inner product thing, and this is what make Hilbert spaces useful. And in fact, inner product, you already know a couple, and one is the dot product coming from Rn. And if you've had some calculus 3, then you know that dot products are intimately connected with geometry and angles and etc. And so the inner product allows you to have a Banach space that also behaves as if it had like right angles in that space. And these right angles are defined by the inner product. So an inner product on a complex linear space. And so when we say that, we mean it's a vector space where the field is complex. This also applies for reals, but when you talk about reals, you just don't need to worry about the conjugate. Where space X is a map. And so I'm going to put angled brackets in defiance of Hunter. I'm also going to do something else in defiance of Hunter. So X cross X to C. So you put a vector here and you put a vector here and it gives you a number, right? So so for instance, if you have X dot Y, it would be the sum of Xi, Yi, right? From Rn. And so this would be the same sort of thing. But since we're talking about Cn, basically instead of having just Yi, we're going to put a bar on the Yi's, which represents complex conjugation. Okay, such that for all, say, X, Y, and Z in X, so more general than just Rn, and lambda comma mu in C, so in our field of scalars, we have the following. So again, this is another spot where I differ from Hunter. So we're going to have lambda x plus mu of y comma z is equal to lambda times x comma z plus mu of y comma z. So just like in our dual product from a Schwarz space, we are linear. And so here we're going to be linear in the first variable. Hunter actually puts linearity in the second variable, and this comes from motivation from the Riesz representation theorem and conventions adopted by physics. He says in applied mathematics, but truly applied mathematicians don't do that as much as he seems to claim, or maybe I'm just in a completely different field. But basically the idea is that functionals can be represented by elements in your space, and so in the Brockett notation coming out of quantum mechanics, they keep the bra, or the first half, as a conjugate linear. And when you do this, basically you can put the functional as hitting a vector on the left. And since the functional itself is intuitively supposed to be a function, we always think of functions coming from the left, then that basically, that's where that motivation comes from. But mathematicians put the the linearity on the left rather than the right. And so yeah, and so I'm keeping with this convention. Anyway, so where does the big problem come from? So if I have x, y, this is going to be y comma x. If you swap the order, you pay with a conjugate. And with this is what you get. You get x comma lambda y plus mu of z is equal to x comma y, or rather I should say lambda bar times x comma y plus mu bar x comma z. And so here we see conjugate linearity coming out of here in the second variable. And so then that means that is where we're going to put our functions for our functionals are going to be coming on the right. Okay, C. What else do we know? Well, x inner product with itself should be bigger than 0. And this is going to be essential for establishing a norm. And the last one is we're going to demand that the inner product with x with itself is 0 if and only if x is equal to 0. So basically what you can do is you can say, well, if x minus y and x minus y is equal to 0, which by the way would be the norm of x minus y squared in Hilbert space context. We haven't gotten that far, but just to let you know. Implies that x minus y must be equal to 0, which implies that x must be equal to y, right? And so this is really essential for Hilbert spaces. And so sometimes you can have what is called a pre-inner product, where this space will end up being larger than just x equals 0. And so you remove this last condition, but anytime you have a pre-inner product, you can actually make an inner product by making what is called a quotient space. But we won't go into that in this class. Okay, so then when you have this, this makes an inner product space. So this makes X an inner product space. And so this is almost where we are with a Hilbert space, but what we need beyond just an inner product space is that we need completeness, and we need a norm that arises from this. So basically, given let's switch back to black. Basically, given an inner product space X with inner product angle bracket X. Sometimes I'll put the X on the bottom here just to make sure if there's more than one Hilbert space floating around. But if there isn't, then I'll just leave it, the subscript off. We can define a norm on X as basically this function which maps X to, say, positive reals, where we let the norm of a vector X to be equal to the square root of X inner product with itself. What we have then is we have some nice things, is that we have the norm of X is equal to 0 if and only if X is equal to 0, right? That just comes from the inner product thing that we just talked about because of that. Also, you get this, X plus Y is less than or equal to X, norm of X plus norm of Y. You also have things like pulling out scalars. It should become the absolute value of lambda times X, etc. And so so then we get a proper metric. So we get a metric on X as basically I'll say d of x comma y is equal to the norm of x minus y. And this is exactly what we see with real numbers. So for instance, if I were to take x and y and say Rn, and the dot product, so x minus y is taken as the n-dimensional dot product sum of xi, yi, then what do we get when we take a look at this difference, dxy be equal to, say, x minus y comma x minus y? This is a sum of I going from 1 to n of xi minus yi squared, right? And square root of that. And so so we see that as just boils down to just regular Euclidean distance in the case of Rn. And so the idea is that this inner product should sort of be like Euclidean space, but ultimately we're aiming for things that are, say, infinite dimensional. So how do we differentiate a Hilbert space from an inner product space? That's easy enough. A Hilbert space is a complete inner product space. And by that I mean when you have a Cauchy sequence coming from your from this induced metric I, then that's what you get. Then you have convergence of that Cauchy sequence to something inside the Hilbert space. Sorry, just had lunch. I'm kind of fuzzed out here. Okay. All right, so the first thing to give, so we actually have a Hilbert space already. We know Rn is in fact complete. It's just fundamental analysis. And so let's see a non-example. All right, so example, non-example. So the classical one to talk about is this. So if we let the space CAB be the space of continuous functions over AB, and we defined, say f comma g, inner product is going to be the integral from, say, a to b of f of x g of x bar dx. This space is not complete. So we have an inner product. Let's define the space, so let's talk about a couple of things here. So first of all, if the integral from a to b of the absolute let's just talk about the first bit. So one thing we have is this: f inner product of itself, which is equal to a to b of f of x squared dx. Because when you put f here with its conjugate, that's just the complex norm. The norm of that complex number. When you take this, if f is identically 0, then you get f comma f is equal to 0, and conversely the other way around, because we know that if the integral of a positive function is 0, then the function couldn't have been non-zero anywhere on the inside. Again, this is a typical thing that you see in your function in your regular analysis class. Now, there's other things that come up. So, for instance, we see that we satisfy all the other inner product things, and so indeed we can say that CAB is an inner product space, but it is not going to be a Hilbert space, and that's because we can find a sequence that of continuous functions that would look like they're converging, but they ultimately won't be. And so how do we want to do this? So if I take this sequence, say here to here, and so I'm going to take a sequence of functions, and it's easier to just describe them with a little graphic here. And so it's a continuous function, piecewise linear, where it's just 0 here, and here is a line, and I need to come up with just the right choice of everything here. So in this case, I'm going to have, I'm going to choose this to be n, and I'm going to choose this to be 1 over n squared. And so the overall area that we have in here ends up being, 1 over n, right? And so if we could take a look, and so this I'm going to call, say, fn of x, and this is going to be over 0, 1. Note that fn of x converges to 0 for all x not equal to 0, but fn of 0 does not converge and diverges as a sequence. So the limit is not a continuous function. It's not defined at the origin. So, I mean, it could be completed, but I mean, that's not what we're here for. So, so then we can go ahead and sort of try to compute this. Okay. I'm just trying to think of the least annoying way to go about this problem, because I could define it piecewise with this, and then like actually just go and compute that. But you know, let's see. Yeah, okay, let's do it. All right, let's get off your lazy butt. All right, so we have f of x sub n is defined in this way. So between, so it starts at n and it drops down to 1 over n squared pretty quick. Let's just go to the next page. So, so keep in mind, we're here, goes down to here, there we go. So n, 1 over n squared, right? And so we know that fn of x, whatever it's doing, is going to be 0 for x bigger than or equal to 1 over n squared. And we know that we have 2 points to connect here. And so, you know, y equals mx plus b, right? So we start, so our b value would be n plus, it's going to be 0 minus n divided by 1 over n squared minus 0 times x. This is for x less than or equal to 1 over n squared. They agree at the end point, so it doesn't matter. And we can do some simplifications here. This is basically going to give us n minus, looks like n squared x, or I think, yep. N cubed x, there we go. right? And if we want, we can write this as n times 1 minus n squared. N squared x. Yeah, whatever you want to do. Okay, so so let's go ahead and compute the integral from 0 to 1 of the absolute value of f of n of x squared dx. And in this case, we are thinking of this as f minus 0, or fn minus 0, right? And so since we're 0 outside of that one region, we're just going to go from integral from 0 to 1 over n squared. And otherwise, we have n minus n cubed x, and this done dx. And so then we can just go ahead and compute that. So we're going to have n times 1 over n squared minus 0 plus, or rather minus, n cubed times x to squared over 2, evaluated at 0 and 1 over, oh man. Oh. Okay, so, sorry, pencil battery died there in the middle of everything. It took me a second to get it charged. Okay, so then the lower bound is 0, and then the upper bound is 1 over n squared. Okay, so then we get is, for the first term, it becomes 1 over n minus n cubed, and then n over 2, and then we end up having 1 over n squared squared, and so this becomes 1 over n minus 1 over 2n. So this becomes 1 over 2n altogether, and this goes to 0. So the idea is that this norm says that we should converge. But this doesn't converge to a continuous function. So not a Hilbert space. And so part of the big reason is that this is an issue is that, continuous functions, I mean, ever since Calculus 1, we were told, like, watch out for holes. If it's holes, it's not continuous, right? And so what we're saying is that we're converging to a function that has a hole at the origin. And so therefore it's not continuous. Is this a big deal? Well, it depends on the context. There is a way of looking at this, and you can define these sort of quote functions from L2, say 0, 1, if you have the integral from 0 to 1 of f of x squared dx is less than infinity, right? And so the continuous function certainly satisfied that, but the thing is that this collection is not a collection of functions. Rather, it is a collection of what we call equivalence classes of functions that basically agree almost everywhere. When I say almost everywhere, I mean that in a mathematical sense. There is a measure sitting around somewhere where if you defer, where one function differs from the other one, if you take that set of points, and that is what we call measure 0, then we say that those two functions are actually the same inside of L2. You can find this definition all over the internet. But it's important to remember, with those caveats, we have that L201 is a Hilbert space, where basically we say that each member in there is an equivalence class, and we can compare and when we want to take the inner product, we take two representatives of these equivalence classes and we throw them into the inner product. The idea is that the inner product is defined through an integral. So having a hole, say in your graph, doesn't matter to an integral, and that's what we call as measure zero. So it'll have no impact, and so that's why we can do that stuff. So L2 is a Hilbert space, but always keep in mind it is not a Hilbert space of functions. It's a Hilbert space of equivalence classes of functions. I'm not going to use L2 too much, maybe a little bit in the discussion today, but basically this is the definition of L2 that we'll be using. And so, heuristically, we'll always think of a member of L2 as being a function, and I might even say an L2 function, but that's not strictly reasonable. Okay, now that is L2, and we have another Hilbert space that is fairly important, and that is this. This is called little L2. So we define a Hilbert space, say little L2 of Z, which is going to be written as a collection of sequences. So we have Zn, and going from negative infinity to infinity, of the sum n equals and this sequence satisfies the sum n equals negative infinity to infinity of the absolute value of Zn squared less than infinity. And sometimes we also think of if I replace this with n, basically this bound would be replaced with 0, and here too. And so you can have little L2 of n, little 2 of z, and I mean they're equivalent spaces. I mean z and n are both countable, and so you can just reorder your sequence however you like. But what's significant is that all separable Hilbert spaces can be written in this way, and so you basically no, well, it sounds like my children are awake. But yeah, the inner product here, before I take a break and lose my train of thought, is this. Basically, we're going to have two sequences, x and y, from a little L2, and this is going to give me the sum of xn, yn bar, n equals negative infinity to infinity. So this becomes a bi-infinite version of what we would typically see with the collection of real numbers. So again, tying back to that connection with a real number system. All right, and well, before the babies get too loud, I better check out. All right, I'll be back in a second. You won't notice the difference. Okay, so now getting back into it. So there's one more example of a Hilbert space to talk about, and this is sort of interesting, and it can actually be extended to infinite dimensional operators. But say we have C raised to the m cross n, so matrices of m rows and n columns, and we have basically for A and B inside this matrix set, a collection of matrices, we have an inner product this way. So A comma B is equal to this, sorry, not sum, but the trace of A star B, where A star is the, say, Hermitian conjugate of A. So you would transpose it, and then you take complex conjugates all the way through. So this is called the Hilbert inner product, and I mean you can also rewrite it like this. So Hunter has the book has this sum I j equals 1 to n of a I j bar b I j. Oh, and we're moving this bar over, and so I should probably also mention so should be B star A according to us. So so this is what we get. This is the Hilbert inner product. And this is also called, and the the matrix that you get when you take the A inner product with itself. The value you get here, which would be, say, the norm of A under this inner product, can be written as I going from 1 to m, j going from 1 to n of the absolute value of aij squared. This is a Hilbert Space norm. Okay, so something that's important to mention here is that this actually extends to a certain class of operators called Hilbert-Schmidt operators, and in fact they're the ones that satisfy more or less this in some sort of infinite dimensional setting. And there you have a slightly different definition of what trace is, and I believe for like higher dimensions, so let's say you have an orthonormal basis, we haven't talked about this yet, but E1, E2, E3, etc. And for, say, little l2, we could have, say, E1 would be 1, 0, 0, 0, 0, E2 would be 0, 1, 0, 0, 0, 0, and etc. So we can talk about operators on the space. And then basically what you get for the trace of, say, an operator, I don't know, say operator T would be the sum, I believe it is T E n, comma E n, for n going from, say, 1 to infinity. And yeah, I'm pretty sure about that. Anyway, but yeah. So, and so then if you have a finite trace norm, so if you take T star T and like that ends up being finite, then you say you're a Hilbert-Schmidt operator. But it's neither here nor there. We're not really going to talk about that much in the class, but I just thought I'd mention it while we're here. Okay, so other things to talk about. So let's get into like one interesting theorem that really that's important here, and this is the Cauchy-Schwarz theorem. So the Cauchy-Schwarz inequality. And so basically it says that if x and y are in X, where X is an inner product space, we have the following. So X comma Y in absolute value, the inner product, it's going to be less than or equal to the norm of X times the norm of Y. Okay. And and so where the norm, it comes from the inner product itself. Okay. So this is a super important theorem. It's used every single time I ever pull out a Hilbert space. And in fact, it might even be the whole point to Hilbert spaces themselves is this sort of thing. Something he doesn't mention here, and it would be nice to mention here, is that we have equality if and only if X is parallel to Y. So that is, there exists some scalar lambda and say C such that X is equal to lambda Y, right? And so, then that would end up giving us equality. So let's go ahead and take a look at proof. Right, so what we really do is we leverage this sort of nonlinearity in the inner product, and otherwise we set up a parabola and find the minimum of that parabola. Okay, so now here, instead of going with the applied analysis proof that they give here, I'm just going to appeal to the textbook Real Analysis, Modern Techniques and Their Applications by Jared Foland. I feel like he does a better job of it. It's a really simple proof, but this one just organizes it better. And yeah, so let's go ahead and talk about it. So first of all, if x inner product of y is equal to 0, then the inequality holds automatically. by the way, if this is 0, then we say these are orthogonal vectors. And now suppose that x inner product y is not equal to 0, and further, without loss of generality, I will assume that y is not equal to 0. So one of these has to be non-zero, and might as well be y. And so now we're going to pick a lambda in C such that norm of lambda is equal to 1, and when we set z is equal to lambda y, we get that norm of x lambda z is equal to the absolute value of x, y. So that's not really that complicated. All I really did is just pick the lambda that's going to rotate our complex number that we get out of our inner product, and just make sure that it's lined up to be positive. Okay, so now what do we do? Well, first of all, we can use a norm property, and so we know that the inner product between x minus tz comma x minus tz is positive, right? That's just one of the fundamental properties of inner products, and so we know positive, and could be equal to 0. And now if I go ahead and expand this out, I can just use linearity on each piece, and then I get x inner product with x minus we have t inner product with z with x. Then we get minus t bar with where we have x x inner product with z, and then we get plus t squared z inner product with itself. Right. Now I'm going to let t be a real number so that we don't have to worry about this conjugate here. Okay, so putting that together, we get x, really what we get is norm of x squared minus 2. Now remember, each of these is norm of absolute value of xy, absolute value of xy. Conjugate and swapping doesn't make any difference for these guys. So it's going to be 2xy in absolute value times t. And now we have plus, now the norm of z is actually the same as the norm of y squared, because basically if we have lambda times lambda bar, and these are both norm 1 vectors, this is equal to 1. So we can take out those lambdas out of there, and it doesn't make any difference. So we end up getting with absolute value y squared, t squared. Okay. So now, just if you recall your, sorry about that. All right. So if you recall your pre-calculus, we end up getting our minimum of this quantity occurs at t is equal to negative b, so 2 absolute value of x inner product with y over negative b over 2a. So it's negative b over 2 absolute value of y squared, right? And so these cancel, and so this is going to be our end up being our minimum point of this parabola that we get in t. Okay. So what do we get when we plug this in? Let's see. So I'll save myself a little bit of writing. So we have this guy. There we go. Plug this guy in. this, and I'll take that too. There you go. And so copy. Right, let's bring it over. Paste. Boom, boom. And now let's do some rearranging. Right, so this guy move up. So that's what we have. And this is where we're going to set t equals 2. And so when you put t in there like that, what do we get? We get this is equal to so we're going to have absolute value of x squared minus 2 absolute value of xy of, and then we put in t, so absolute value of x comma y, boop, over by 2y squared, and then this plus by 2y squared times this, so we have absolute value of xy over 2y squared. All right. And that's squared. Okay, so what do we end up getting? So we can do some quick simplifications. Absolute value of x squared. So minus 2 times, looks like absolute value of x y squared divided by y squared on the bottom, plus putting this through, we get xy inner product squared divided by y squared on the bottom. When that cancels, then we add one more of those guys, then we can combine these two guys, and so we get combining coefficients. Man, was the last time I said that phrase? All right, over y squared. All right, boom. Whew. All right, so that's what we get. We get this guy here is bigger than or equal to 0, right? So now with just a couple of rearrangements, so I can move this guy over and then multiply over y squared, you get the result. So, okay. So that's nice and handy, and this is one of the core results of Hilbert space theory. It's something that you use like every single day when you're dealing with Hilbert spaces and inner products. It is your fundamental inequality. Okay, so let's keep going. Let's see. So in applied analysis, getting back to there. So they're talking about, say, theorem, what they call, say, 6.9, and this is nice. I'm not going to prove it, and they don't give much of a proof in here either, but it's just something nice to know. But usually we start kind of the other way around with this, but yeah. So a normed vector space X is an inner product space with a norm derived from an inner product if and only if we have the absolute value of x plus y quantity squared plus the absolute value of x minus y quantity squared is equal to 2x squared plus 2 normal y squared. Okay, so this is called the Parallelogram Law, and basically when you have that, you have an inner product space. So essentially, people draw this figure, shoop, and so so basically what you have is you have this, and this is x, or let's say this is y, this is x, and then this would be x minus y, and this would be x plus y, And so if you read this, if you take this parallelogram and you add these four sides, the square of these four sides, and then you add the square of these two sides, these two diagonals, then they're the same. And so so this is yet another geometric intuition that comes in from using Hilbert spaces. You can look at the proof and the text if you like. It's only like 3 lines, and it's more of an important result to know than anything else. But it truly, I've never been in a situation where I didn't know what the inner product was in the first place, and so having the inner product, all this stuff really kind of falls together automatically. Going backwards is trickier, but then again, I mean, like I said, I almost always know that I have an inner product, so I'm not going to bother with proving that here. So yeah. Then there's also a slightly another small result here. This is his theorem 610, and it basically says, or if we let X be an inner product space, then the inner product is continuous, is a continuous map from X cross X to C. And this really follows from Cauchy-Schwarz. So say the proof, if you take, say, x1, x2, y1, and y2, and x, you get this pretty quick. So it's going to be x1, comma y1 minus x2, comma y2. So so the image of our function. This, it can be rewritten like this. So if I were to, say, add and subtract, say, x1, y1, and I add, say, let's say subtract x2, y1, and add x2, y1, I don't change anything, x2, y2. But what I can do is I can use linearity of the inner product, and so I get x1 minus x2, comma y1, and then I get minus x2 of y1 minus y2, or sorry, y2 minus y1. Nope. Hold on, just give me a second. Sorry, plus y1 minus y2. Sorry, brain fart. Anyway, triangle inequality lets me do this, and then Cauchy-Schwarz inequality lets me do this. So this is r of x1 minus x2 times y1 plus norm of x2 times y1 minus y2. Okay, so now I see that if I have the sequence of, say, x, if I have something like x comma y as a point in x cross x converges to, say I have xn, yn converges to some x comma y, then I see that these x's are going to go to 0, and these y's are also, the difference between these y's is going to go to 0, and so then therefore this goes to 0, and therefore we have continuity, right? So anyway. So yeah, so we can just stop here. Okay, cool. So yeah, so that's that. So a lot of these are really just sort of basic fundamental things I just wanted you to get an idea of. The next part is really kind of the where we finally, one of these other places that we get this geometry coming back into, and this is section 6.2, and we're talking about orthogonality here. And this is really fundamental to all of Hilbert space theory, and is really why Hilbert space theory is a good thing. And so we saw before some things that we would call orthogonal sets. For instance, if we took, when we were taking a look at Fourier series, If we compared, say, e to the im theta with in theta, we saw that they're sort of, if we multiply their, take one, multiply by a conjugate of the other, and we integrate over the circle, we ended up getting either 0 or 2 pi, right? And that basically says that they're orthogonal if n is not equal to m. Right, and so we would like to take this idea of orthogonality that we saw there in Fourier series, and then again that we know from say real numbers where we just have right angles, and the idea of Hilbert spaces to generalize that, and so that's what these definitions are aimed at doing. Okay, so we start with this definition. So it's definition 6.11, and it says that if x and y are vectors in H, then a Hilbert space, then we say x and y are orthogonal which is written as x orthogonal y, if x inner product of y is equal to 0. And more generally, we say A and B, which are subsets of H, are orthogonal when say, how do they say it, x and y is equal to 0 for all x in A and y in B. And we writing all this notation A perp B. Okay, then we say the orthogonal complement of A in H is written as A perp, which is equal to x in H such that x is perp y for all y in A. Or if we want to use our new notation, we would say it's a union of all singleton sets of x and H, such that singleton set x is perp to A. Yeah. Anyway, though don't ever write this. This is really the definition that we want to use. Okay, and so theorem, the orthogonal complement of a subset of a Hilbert space is a closed linear subspace. Okay, so there's a couple ways to show this. First of all, I'm going to cheat a little bit and just use some basic analysis here. So we know that the mapping is so let's go ahead and start here. So we have A is equal to A perp is equal to x inside of H, such that x in a product of y is equal to 0 for all y in A. Okay. So first of all, we can show it's closed. So let xn go to x. It'd be a sequence in A, then we can show that, yeah, sorry, there should be, let x edge for a sequence, sorry, trying to be precise, xn n equals 1 to infinity subset of A. There we go. And we'll say it converges to something in H. So basically what we know is that we have, we're taking a look at the limit as xn goes to infinity, as n goes to infinity of xn inner product of y. And what is this? This is just, we're trying to figure out what is x inner product y, and we want to show this equals 0. So then that would tell us that it's closed, because a closed set is one that contains all of its limit points. So since the inner product is continuous, we can pull out the limit here, and then we get xn comma y, and then we just have the limit as n goes to infinity of the 0 sequence, just because xn is in a perp, and y is in A. So this is equal to 0, and so equals 0. And this is for y and A, we get this, and so since y was arbitrary, that means that x must be perp to everything in A. So thus x is perpendicular to A, and x is in A perp. All right, so now linear space, that's pretty straightforward. So we're going to let x comma y be in A perp, and let mu comma lambda be complex scalars. Then we have, for say z in A, we get this. We have mu x plus lambda y inner product. I'm sorry, it's my bad habit. Inner product with z is equal to mu A inner product with z and plus lambda of y inner product with z is equal to mu times 0 plus lambda times 0 is equal to 0. Right, so what we see then is that for any arbitrary z, we have the linear combination is going to be orthogonal to it, and so then therefore we have that mu x plus lambda y is in A perp by definition, right? So quick and dirty, but that's more or less the proof. Okay, so let's go on to the next thing. So now we're getting to slightly more important results, and it is this. So now we have our projection definitions, our orthogonality definitions. We can start talking about projections. So this is Theorem 6.13 in the book, and is a projection theorem. And this is really important for approximation theory. So we're going to let M be a closed linear space of a Hilbert space. So linear subspace of a Hilbert space. So it basically is a subset of a Hilbert space that contains all of its limit points. Basically we have these two ideas. We have one for each x and h. There is a unique closest point y and m, such that we have x minus y is equal to the minimum over all z and m between x minus z. Right, so if we take a look at all the distances between x and a member of m, there is a point y that satisfies this. All right, and b, the point y and m closest to x in M is the unique element with the property that x minus y is going to be perpendicular to M. So it's going to allow us to decompose every vector x into 2 points. So we can say basically it's going to be y plus x minus y. Now this equality seems trivial, but basically what we're saying is that this guy is going to live in M, and this guy is going to live in M perp, and this sort of breakdown is extremely important. So, so that's what we're saying. Okay, so so then we can go ahead and start working out exactly how this goes. Okay, so let's go ahead and take a look at the proof. And this is where my dismissiveness at the parallelogram law comes back to bite me. All right, so what we're going to do is first we're going to let D equal the infimum over all x minus z such that z is in M. All right, so this is that minimum distance that we were talking about, and the way we know that D is well defined and not say infinite is that we assume that M is a subspace, and so since it is a subspace, it has to contain at least the origin, and so then therefore it is not empty, and so then therefore D has to be at the very least the norm of x. So it's probably smaller than the norm of x, and in fact it is, and that's going to lead into the Pythagorean theorem later. So there we go with that, and so now we're going to let yn be a sequence in M such that we get this. We get the limit as n goes to infinity of the absolute value of x minus yn is equal to D. Since we know that this is an infimum, there must be at least a sequence that's going to go all the way down to D, although we have no guarantee that it's actually going to achieve that, and that is really the crux of the proof here. Okay, so thus, for all epsilon greater than 0, there exists an n such that for all n greater than or equal to n, we have that x minus yn is less than or equal to d plus epsilon. All right, so now we want to show that yn is a Cauchy sequence. So something I should say is that M has been assumed to be a closed subspace, and since it is a closed subspace, it makes it a closed subset of the Hilbert space. We know that the Hilbert space itself is complete, and so then since the Hilbert space is complete, every closed subset of a Hilbert space of a complete space is itself complete. So therefore, if we can show that this is a Cauchy sequence, and that means that this Cauchy sequence must converge back in M. So this is the undergraduate topology reasoning that you would have to go through this, but they sort of brush over it. Okay. So now we want to show this Cauchy sequence, and this is going to use the parallelogram law. So from the parallelogram law, we have the following. We have ym minus yn squared plus 2x minus ym minus yn squared is equal to 2 times x minus ym squared plus 2 times x minus yn squared. So basically what we're doing is we're have these two vectors x minus yn, x minus ym, and then the other side is going to be the difference of these two, the difference in the sum of these guys. So, so that's what gives you this stuff on the right. So, oops, there we go. So now, following our nose, and the book. So since we have that ym plus yn divided by 2, basically what you get when you factor out 2 here, is in M, because M is a subspace. This gives us this x minus ym plus yn divided by 2 has to be bigger than d, just because of the enfeeblement property that we have up here. So that means if I go ahead and leave this guy in here, I have this. So I get ym minus yn quantity squared. I'm going to move this term over on this side, and so I get 2 times x minus ym squared plus 2 times x minus yn squared minus, now pulling out 2 here, we get 4 norm of x minus ym plus yn over 2 squared is going to be less than or equal to 4 times d plus epsilon squared minus 4d squared, and ultimately this is less than or equal to 4 times epsilon 2d plus epsilon, right? So, good news. If we choose epsilon to be small enough, then we can make this quantity as small as we'd like. And so that basically means that we have yn is Cauchy. Cauchy. Okay. So then that means, thus yn converges to y, and from our discussion earlier, that has to be back in M, because M is a closed subspace. Even subset of a complete metric space. Okay, cool. So we have the existence of a minimizer. That's fantastic. All right, so now the uniqueness is going to be the next thing. All right, so for uniqueness, we again use the parallelogram law. So assume that there exists a y and a y prime in M such that x minus y is equal to x minus y prime is equal to d. So now we're going to appeal to the parallelogram law exactly the same way again. So we have 2 times x minus y squared plus 2 times x minus y prime squared, so the sides of the parallelogram, is equal to 2 minus y prime 2x times y minus y 2x minus y prime squared plus y minus y prime squared. So same setup as before. And something to note is that if I go ahead and rewrite it like this, I can so I can isolate this piece here, and so I'm going to get y minus y prime squared is equal to 2 times x minus y squared plus 2 times x minus y prime squared minus 2, and now let's just say 4 times x minus y plus y prime over 2 squared. So this term here is still in M because it's a linear subspace, and so this has to be bigger than or equal to d, and this one is equal to d, and this one is equal to d. So then what you get is you have y minus y prime squared is going to be well, so we have 2 times d squared plus 2 times d squared minus 4 times something bigger than d squared. So then you get this is less than or equal to 0, but that means that y minus y prime must be equal to 0 because norms can't be negative. So there you go. That gives you that y is equal to y prime. So uniqueness follows. Okay, so now the last bit comes down to showing this orthogonality of x minus y. Okay, so for the orthogonality of, say, z is equal to x minus y to m, we can get this pretty quick. So what we're going to do is we're going to take a look at the function. So we're going to let, sorry, a u be an m, and without loss of generality, I'll assume that z inner product with u is is real. Okay, and this can be done by multiplying by unit value and c, right? So just like before. So now what we're going to do is we're going to set f of t is equal to the norm of z plus tu squared. And we can go ahead and expand this out. And so we're going to get, say, norm of z squared plus 2 t times z inner product with u. And then we get plus t squared times norm of u squared, right? And so what we can tell about this guy is that f has a minimum value at t equals 0. And how do we know that? Well, since z is equal to x minus y, that says that z plus tu is equal to x plus, say, x minus y minus tu, and this is inside of M. So the smallest that this could possibly be is when t is equal to 0, because all the other ones are not the unique value y that makes this the minimum. So so that is our sort of explanation of that. So this implies that f prime of 0 is equal to 0 is a local extrema. And if I take the derivative of the left-hand side, I get 2 times z comma u, and is equal to 2t, plus, so f prime of t is equal to 2 times z comma u plus 2t times norm of u squared. And I know that f prime at 0 is equal to 0, and that is equal to just 2 times z comma u. And so that tells me that z is orthogonal to u. And since u is arbitrary, that says that z is inside of M perp. And there we go. This last bit came from Foland again. So yeah. So that's that. So this is a bunch of the core ideas of Hilbert space theory, and there's still a couple more things I want to get into, and I might insert another lecture building those things up, namely Pythagorean theorem and orthogonal bases, and then after that we can start talking about reproduced kernel Hilbert spaces. So yeah, I'm gonna stop here for now, and yeah, take care. Okay. So that got us most of where I wanted to get to today, and that was defining inner product spaces and sort of the perp space for a closed subspace. Next time we're going to talk about orthogonal bases and discuss how we can sort of
get a sort of breakdown of a function inside of Hilbert space in terms of these things. And this will sort of build on this idea of orthogonal spaces and sort of separating things out that way. And I guess thank you for watching, and I'll see you next time.